Alright, we had a student last week who was working on an honors project problem, and he called it the nature of infinity. And that was Christian Smith. Did a real good job with it. What I want to do is further clarify this issue to help him as he moves toward doing his presentation at the state level. So this is kind of for you, Chris, but for me too, because I thought this was really interesting. And what the issue was we run into a problem. So here, what we do, we're concerned with volumes of revolution. Volumes of solids of revolution. Okay, so we take these solids here, rotate them all around, and find the volumes of those little cylinders, and then we do infinitely many of those, and that approximates the volume really well. Actually, as you take infinitely many of those and take the limit, it probably approximates the volume exactly. But then we started dealing with surface area of solids of revolution. And you would think if you can do this method here that we just spoke of, rotating these rectangles around, this is line y equals x, by the way, rotating those rectangles around, and you can get the volume. It seems like then surely you could rotate around and find the surface area of each one of those things, and you would get the appropriate surface area. It turns out not so fast. Okay, and Christian had asked me about this in class, and I was stumped, to be real honest, why this would work for one and didn't work for the other. So, but now we have a resolution. So let me kind of talk through how to work this problem out and get a definitive solution. So let's look at this. Here we have the line y equals x, and we're going from 0 to 1, and we're going to talk about the volumes revolution and the surface area of the when we revolve that thing around. So let me draw some pictures here. Okay, so let me show you where the issue lies. I'm going to go in yellow here. I'm going to call this little open space there E1 for error. So what we really are talking about here is the error. E2 and E3 there. And what I would like you to do, Christian, is actually figure out what E1 is. What does E1 equal in this particular case where we have delta x is what, 1/3? Figure out what E1 is, and then E2, E3. But then what you really want to get is a general term for E sub n when n is arbitrary. Okay, and not that difficult to do. And that is, well, yeah, let's just do it like this and do it for the areas there, and you'll see that the area under the curve, you should see that when we take the sum of the E sub n's, we take the limit as n goes to infinity of the sum, and see what you get there. Okay, and then when you're done with that, what you'll want to do is to take let's look at E1, and then let's rotate it around and form that little piece right there, and talk about let me go in a different color now. So let's go here, rotate it around, and let's find the volume. Say volume of E1. So up here we were finding the areas. This was area up here, because we're just finding the area between the rectangle and the curve. But now we want to rotate it around and find the volume. So rotate that one around, find the volume. Rotate this thing around, so it's like a cylinder with its with a hole like right in the middle of it. It's what you're going to have there. And to get the volume of that, so the volume of E2, what I encourage you to look up is the theorems of, I believe it's Pappus of Alexandria. You will like this, one of our old timers, and he uses center of mass to find the volume. So then in general, find a volume for an arbitrary term, E sub n, and then you want to take the limit as n goes to infinity of the sum of all those volumes, oops, E sub n. Okay? Next move. Next move, let me go in red here. Well, I've already used red. Let me go back to white. Okay. Next move, we'll take those same rotations here, rotate those things again, but now I want the surface area of once you've rotated each one of these around. Rotate this one around. So taking that thing, rotating it around, and find the surface area. And again, I would use the theorems. Go and look up theorems of Pappus of Alexandria. First of all, it'll be cool. It's interesting, and he uses the center of mass of each one of these, which makes it pretty neat. And we want to find the area, surface area of E1, surface area of E2, dot dot dot, surface area of a general one. Okay, surface area of, I should have put surface area E sub n. And finally, what you want to do is take the limit as n goes to infinity of the sum of all those surface areas. And you're going to find a very interesting result when you compare this to this. Okay, very interesting result that really is like where during the presentation where Christian proved that pi equals 4. Similar thing here. Anyway, I think that will let you tighten this thing up and give you a good analytical solution to this problem, at least for this example where the function y equals x. And we could do it for an arbitrary function as well. The very similar argument would work. But, cool? Alrighty then. See you guys out in the field.